So, you may recall that we were solving this problem, and we were really kicking its ass. So, I expect that we'll have no trouble finishing it. Remember, we have 6 steps in our process, and 1 and 2 were done for you, for us, by me. So, in other words, for you. At the before we even started. So 1/3 of the steps. Can you not see that? Good call. I don't know how that turns out. It's like supposed to go on standby.
It works for a lot of things. I wonder what type of engineering.
Yes. That method never gets
like when you beat on stuff and it starts to work.
Yeah.
Why does that?
It never gets debunked, even when you get a PhD in mechanical engineering.
Yeah.
Still, like, nobody ever is like, you know what, hitting the thing is a bad idea.
They never say that.
It's called percussive maintenance.
Should we just be like hitting everything?
But why does that always make it work?
Works surprisingly well. Not really on digital stuff as much now, but old stuff it works really well. Okay, so we were solving this, and we were like, step 1 and 2 are done for us. Steps 3 and 4 and 5 were easy. We just wrote down 4 equations, 2 elemental equations, a KCl equation, and a KVL equation. And then we got to step 6, and we did, that one breaks out into multiple parts. A was to eliminate 2 of our variables using KCl and KVL. We did that. And then part B was to eliminate the remaining variable that wasn't showing up in an equation with a time derivative, and that wasn't an input, which was IR. We eliminated IR, and we got this expression. So we want to solve this ODE. Let's rewrite it in a form that might be a little more familiar to us, which is to bring RC, well, let's define RC to be tau, the time constant. So let's just define that. And then we can multiply both sides by tau. So we get tau dvc dt. So tau. I'm just going to kind of fit it in there. And left over on this side is Vs minus Vc, but we're going to add Vc to both sides as well. So we get this expression. Pretty good. Who here feels like they've seen these before and done them at this point? First order, ODE, linear, probably even use tau in there. It's pretty standard stuff, right? So we know how to do this. So we could pretty much auto-calc the rest of this. But anybody ever play a video game where you can auto-calc a battle? Like you could manage it yourself, or you can be like, nah, I'll just let the computer decide like who would win in this, because you like have other things going on. It's great. It's a video game that plays for you.
Like simulate to the end.
Yeah, it's like my kind of video game. So okay, what is the first step when we solve? So there's a few ways you can integrate this equation, but I'm not going to do that because I want to use the method of undetermined coefficients, which applies not just to first order systems but to higher order systems. So I want to show you the general solution method, and then you can apply it to any system, any order. So the first step is to find the what solution?
Homogeneous.
Homogeneous solution. So there is an E in there. So homogeneous solution. And the first aspect of that is to find the characteristic equation, right? There's another name for it people use. Do you know what it's called?
Characteristic? Particular?
No. We'll figure it out. Somebody will be like, oh, I remember in my x class, we called it this. So we rewrite the differential equation, but the characteristic equation is going to be tau times, whenever you see a time derivative, that's a lambda. If you see a second time derivative, that's lambda squared. Third time derivative, that's lambda cubed. We have a first derivative, so we just have a lambda, plus lambda raised to the, how many derivatives are there on that? 0, right? 0 time derivatives on VC, so lambda to 0 is just 1, or as I like to put it, just 1. Equals 0. Okay. Right-hand side of characteristic equation is always 0. Doesn't matter what's on the right-hand side of the differential equation. Assuming we've rearranged it so that all of our independent variable terms show up on the left-hand side. So all of our VCs need to be on the left-hand side. And then we can zero out everything on the right-hand side because that's all the input or the forcing function, or otherwise termed. So I know this equation is very daunting to solve for lambda, but I'm going to go out on a limb and say we could all find that it's negative 1 over tau. Okay. You might wonder why I say ta sometimes instead of tau. And I've had long debates with people about this. So there are two ways of pronouncing the Greek letter ta or tau. And I've typically used ta because I was in, I guess I think you're like a life member, I don't know. I was involved in the Engineering Honor Society, ta beta pi. And everybody in that calls it ta beta pi instead of tau beta pi. So that's why I use this pronunciation. I know you wanted to know that, and it was important for us. So there you go. All right, so, ooh, blank page. So what do you guys think? Are we prepared to find the homogeneous solution now that we have the solution to the characteristic equation? Yeah, so we have VC, we're going to call it VC homogeneous, so we'll denote that with another subscript H of T equals, remember that what you do with your lambdas is you take a sum of constant terms. We're going to use kappa as our constants. I'm going to try to make it clear that it's a kappa. Kappa and e to the lambda t. Now, if you had a second order partial or a second order differential equation, then you would have two solutions for lambda. It would have been a quadratic polynomial on this side, and you would have had two lambdas. And then you would say that it's kappa 1 e to the lambda 1t plus kappa 2 e to the lambda 2t. This is true unless you have repeating roots of your characteristic polynomial. So if you've got lambda squared in here, but it ends up that the two lambdas are the same. If you have repeating roots, remember you got to add that t out front. Solution, even for your homogeneous solution. Yeah, this is all sounding familiar, I'm sure, to you. And you're like, oh yeah, there's that exception. Don't forget about that. In any case, this is what happens. Most of the time you don't have repeating roots, and you get this. I'm using kappa and not C because kappa, because we use C for capacitance, and it gets confusing. So I use kappa, and then I'm going to use K in a minute. So gotta differentiate between them. Okay, so there's our homogeneous solution. We don't want to determine. I guess we could plug in what lambda is. Kappa e to the minus t over tau. Good. So that's done. Don't need to plug in any initial conditions. If we did, we would probably get the problem wrong, although there is a way to do it that way. But I'm not going to go through that method right now. We'll do it like next semester. Or maybe this semester at the end. We'll see. All right. So step 2 is to find the particular solution. Now, we're using the method of undetermined coefficients. So that method requires you to look at what the input is, the right-hand side, and say, what is its functional form? In this case, we said that Vs was just going to be a constant 12 volts. Okay? So when you have a constant input, then the assumed form of the solution is Vc, particular solution, is not kappa, K1. So our input is a constant, so we assume that we can find a particular solution that is just a constant. There's a table in your differential equations book. Undoubtedly, there is a table for sure in the system dynamics textbook of common inputs and then the form of the particular solution you should assume. Now, this is the method of undetermined coefficients, and that's why K1 is undetermined right now, so we need to determine it. So when we're done with it, it'll be a determined coefficient. And let's find what K1 has to be. We're positing, we're making a claim that VC particular is a solution is, we just put in a constant, a constant is a solution to this differential equation. And so in order to determine what that constant is and to verify that there is such a constant that satisfies the differential equation, we just plug it in. So we say, okay, ta times, what happens if I plug in K1 for VC here? Yeah, time derivative of K1 is 0. So this isn't tau as a function of 0, it's just tau times 0. Plus, what's the other term? VC, which we're saying, we're assuming there's a solution that is just K1, right? And that's equal to Vs. We should plug in something for Vs. I'm going to plug in, instead of 12, I'm going to put V0, and I'm going to define V0 as being equal to 12 volts. But I don't like plugging in numbers until the end, so when I see a number that I need to plug in, like to find the particular solution, I just substitute a symbol in for it, and then at the end I can plug the number in. But it's better to do it this way, because then if I turn around, I'm like, what would happen if it was 5 volts? And you'd be like, I gotta go back and do half the problem again. And you also don't recognize how that input affects the output, because the number is already plugged in. So that's why we do it this way. So we say, okay, it's just V0. Something like this is in your homework too, when I say the initial condition for the voltage across the capacitor is VC0. Remember that in special problem 1 or something? Hopefully you guys are working on it. Because until yesterday, it was due today. So in any case, yeah, I say it's equal to VC0, which means, and I say it's VC0 is a real number. It's just some, like it could be 5 or whatever. It's just some number. All right. So I feel like this equation is another one that we, it would take us some work, but we could figure out how to solve for K1 in it. What do you think?
Yeah. Divide by 12.
Yeah, so it's just 12 volts. It's just VO, right? V0. All right, so that is our determined now coefficient, K1, which means that our particular solution is VC particular of T is just this VO or 12 volts, right? Well, that was pretty easy. Let's see if we can't find something harder. Let's find what's called the total or the general solution. So there are those two names for it. I usually call it the total, but the general solution is also very common, which is just defined to be, and I usually don't give it a subscript, so VC of T equals just the homogeneous solution plus the particular solution. Well, that wasn't very challenging at all, was it? Jeez. Can't find anything challenging in this problem. So VC homogeneous is, from up here, kappa, we haven't figured out what kappa is yet, right? Kappa e to the minus t over ta plus VCP is just V O, right? So we've got, I just dislike that kappa looks like a Disney
It says
script.
negative t, right?
Sorry, what was that?
That's e to negative t, right?
Yeah, that is a negative in there. I don't know if you can see it. Negative t over top. Good. So this is our general or total solution, which is a family of solutions, right? It's a different solution for each kappa. And how we find what the solution is for our specific problem is to find the, you guessed it, specific solution, which we find by applying the initial conditions. Okay? So the initial condition given was that VC at time equals 0 is equal to 0, right? So let's just plug that in. So VC at time equals 0 is equal to 0, which implies that 0 equals kappa e to the 0, which is just 1, plus V0. Another mind-bogglingly difficult algebraic expression to solve, algebraic equation to solve, that tells us that kappa is equal to, I'm like, I should just go work for Walt Disney, I think. Kappa equals what? Great. Cool. So then we can write our solution, our specific solution, as VC of t equals, now we know that kappa is negative V0. We plug that in, notice there's a V0 in both terms, right? We're going to want to just factor that out, and once we do that, we have V0 times, I'm going to switch the order of these terms too. So if I factor V0 out of the second term, I get 1. If I factor V0 out of this first term, there's negative V0 there, so it's minus e to the minus t over ta. And that is our solution. However, I did ask not for the voltage across the capacitor explicitly. I asked for the voltage out, which is the same, right? But we should say explicitly that our V out is equal to VC of t, which is solved for us. We don't need to rewrite it. Excellent. We should sketch these things. We solve these problems. We should sketch them, get a feel for what they're like, right? So this circuit, remember we talked through, we had like this idea that if we apply this constant voltage and the capacitor wasn't charged up to begin with, it would charge up and it would approach some steady state value that we think is 12 volts, right? That was our guess. It should start at 0. Now let's go ahead and plot. Now we've got an expression for the function. And let's take a nice gray line here. We're saying it should go to 12 volts, V0, and it should start at 0. So I like green traces. So it starts at 0 because at time equals 0, we get V0 times 1 minus 1, right? So 1 minus 1 is 0, and we start off at 0. As we increase time, this exponential decreases, and we are subtracting less and less, okay? So 1 minus that number that's less and less is going to approach 1, and we're going to be left with V0. So, and it does that exponentially, we see now. something like that. And it gets pretty close, but does it ever reach v0? No, technically not. Well, in the limit, right? As time goes to infinity. But that's no finite time will it reach v0. And yeah, so that's pretty much the solution for this. This is what the output voltage is a function of time. We went through all the steps. I mean, so it was pretty easy to solve this differential equation, right? And it's really similar to the one that is, well, the special problem has a sinusoidal input. We're going to do that. This is the next problem. But it's the same exact process, right? The algebra gets a little bit harder, but that's the only thing, right? And we all know how to do algebra. Sometimes we get scared, but that's the only reason why we won't be successful. It's really just a matter of applying the same process again. All right. So that was that problem. Any questions before we move on? Okay.